And welcome back. Now today we're going to go back to basics because I've discovered this little tiny transistor here which I didn't know existed in this format compared to this one here. What are the two differences between these two? Well, basically the one on the right, that's the one with the white top that I put there so I could recognize it. This is a general purpose NPN transistor that's used for driving relays and buzzers and all sorts of things. And it's a general purpose one. You can use one, you can use the other. This is a BC548, but you could use a BC547. You could use a 2N2222. I mean, there's quite a few to choose from. And they're all pretty much the same. There might be some minor differences in the current carrying capability of it, or the power dissipation, but in general, for most things, they're pretty much interchangeable. This video was sponsored today by PCBWay, PCB Prototype the easy way. Design your custom boards and submit them via the PCBWay website. You can put your options in, very easy to do. I managed it, and within a few days I got my package with 10 pieces of a 2-layer board for just $5. The quality is excellent. Go on, have a go. Order from their website now. And then I discovered this one here, and it's whilst I was doing my workshop heater video that I discovered it, or rather after I did it I discovered it, because in my workshop heater video you may have noticed that I needed to drive a couple of relays like this because the GPIO pin of the Arduino was insufficient to drive this by itself. Although it's a 5-volt coil on here, 5 volts DC, the current was too much. I think it was something like 70 milliamps, and as you know, the GPIO maximum for an Arduino is 40, but you can't drive them all at 40, so generally you tend to limit it to about 20. Well, 20 is quite a bit away from 70, isn't it? So I used one of these little transistors here, and it all worked fine, as you'd expect. I mean, after all, it's just being used as a switch. And then after I'd completed all that, I was just browsing the internet, and this little beauty here popped up. Now this is a MOSFET, and it's in a TO92 package, exactly the same shape as this one here. And I thought, I didn't know they existed. I assumed MOSFETs for carrying current, you know, large amounts of current, were all like this. Big, chunky, they're pretty easy to use, but they are quite big. And of course you can mount them onto a heatsink if you really want to. If you need to, quite often you don't need to. That's the whole point about MOSFETs being very, very low resistance when they're on. And I thought, well, that's what I'm used to, and yet you can get them in these little TO92 packages. So I bought a pack of 10 from China, and I thought I'd give it a try. And while I was experimenting, I thought, well, I might as well tell you guys about it in case you're wondering as well. So, as I said, this is in fact a 2N7000, and the current capability of this one is not quite as great as this one actually. It's 200 milliamps and 350 milliwatts in power. Now, the thing about MOSFETs, well, those ones at the back there, is that we choose them because we want to give source or sink a lot of current. And if you sink or source a lot of current, then if there's any kind of resistance inside these, it's going to get hot. So the resistance of these bigger ones, what's known as the RDS on, that's the drain to source resistance when it's switched on. What is the resistance? Well, normally it's something about 0.02 of an ohm. And while small, it's not nothing, so they can still get hot if you're sinking lots of current, you know, 10, 15 amps. But for most purposes, they don't get even warm. So I'm thinking, okay, 0.02 of an ohm, what's the RDS on for this one here? And the answer is a maximum of 6 ohms. It doesn't tell you what the average is, and it doesn't tell you what the minimum is on the data sheet. And I'm thinking 6 ohms? That we'd be laughed at if we started to use these big ones with a resistance of 6 ohms. The power dissipation of these would, you know, it'd light up your room. So what's the point of having a 6 ohm resistance in here? Well, a maximum of 6 ohms. Does it actually work? And more to the point, can we drive it like we can drive these other ones directly from the pin of an Arduino? which is to say these big ones switch on at a 5-volt trigger voltage onto the gate. Will this one switch on with a 5-volt trigger voltage? And is it in what way is this better then than this BC548 that's done us so well over the years? Well, time to switch the circuit up a bit and we'll have a chat. So the circuit is really simple, and it's this one down here. So we've got the 2 transistors, MOSFET on the right, exactly the same circuit for both. So we're having a load, this one being the MOSFET, into the drain, and on this one we're having the load into the collector. Both are being connected to ground via this source or emitter, and this rail at the top is going to be 12 volts because 12 volts is a useful voltage to be able to switch, basically. Quite often we use 12 volts within Arduino projects, but of course the Arduino itself is only 5 volts. So what we're going to do is trigger each of these transistors with a separate 5-volt supply in that direction, so the current will flow like that. So we're going to ground the 12 volt and the 5 volt together, but they will be independent supplies, just so there's no interference between the 2 voltages. Now, as you can see at the back there, this bulb is sort of glowing, but it's not particularly bright. That's because I'm running it at 5 volts at the moment via the MOSFET, and it's 124 milliamps. Well, I can tell you that without any kind of transistor in the way, this would take about 220 milliamps. It's a 12 volt, I think it's a 2.5 volt or 3 watt bulb. It doesn't really matter what it is, as long as it can be supported by the actual transistor. We're not really worried about that. After all, this transistor and this one, they're all sort of pretty low level stuff, you know, 200-300 milliamps. You can get higher versions. Let me see now. The equivalent higher version of the 2N7000 is BS170. The difference is it can take 500 milliamps. Not bad, but I haven't got a BS170 to test at the moment. And this one can take, as is, that can take 500. So I suppose in some ways the BS170 would be a better match for the BC548. But as I say, to switch a coil or something in a relay, you just don't need that much. Probably 150 milliamps maybe. So what I'm going to do is ramp up the voltage, and we just see how much current that bulb actually takes, considering it should take about 219 milliamps at 12 volts. I'll put the camera on the power supply so we can see what's happening. Right, so in the top left of the screen you can see the output from my power supply, 5 volts, 124 milliamps, and this bulb here is sort of glowing. Let's wind that up a bit to 12 volts and see what we get. So it's now at 12 volts. The bulb is appreciably brighter, and this is probably about the brightness it would be in real life. And we're taking 210 milliamps. Now this transistor is actually only rated for 200, so I'm overdriving it at the moment. And just a quick finger test, it's not getting hot, which is great. Now I would have thought, given the potentially high resistance of 6 ohm, although that is a maximum we must remember, I would have expected some sort of warmth, but no, it's absolutely fine. So what have we proven here? Well, we've proven that the MOSFET can handle 210 milliamps and it doesn't get hot and burn up. But then again, so can this transistor, surely. About time we connected this one up instead and see if there's any difference and what the internal resistance of this transistor is compared to this one, so that in that 210 are we going to actually get a few more milliamps flowing through it with the BC548. Let's find out. Right, so all I've done is connect the bulb up to the other side, the collector now of the BC548, and I'm about to apply the separate 5 volts to the base for a little limiting resistor. We want 2 or 3 milliamps to flow through here, so I've got I can't see what that is from here. It's probably about 180 ohms or something like that. Oh, butterfingers. Right. Now that's quite interesting, because now we have 215 milliamps flowing through there. Now this can take 500 milliamps, so we're well within the capacity of that transistor. And in fact, you could argue now that because we're taking 5 milliamps more through this, well, 4 at the moment, seems to be dropping a little bit, this is actually a better bet than the MOSFET. Or at least they're working pretty much the same. So why choose one over the other? And that was really my question, really. Even before I started all, I thought, well, why would you choose a MOSFET in a TO92 package that can only sink about 200 milliamps over a standard NPN transistor that can sink actually a bit more, well, double in this case, and have been serving us very, very well for years and years? Why one or the other? Well, let's think about the advantages of a MOSFET. And for this, I'm going to Wikipedia because I thought, well, I don't know why you would choose a 2N7000. So it talks here about the two ones we've already mentioned, the 2N7000 and the BS170. Okay, fine, yada yada. What exactly are the advantages then of one over the other? So it says here the advantages of the MOSFET are: 1, you don't need a gate bias. Fine, okay, we don't have to connect the gate to the positive supply via a limiting resistor initially to switch it on at all. And in addition to that, the gate has such a high input impedance that it takes almost no current. However, I would temper that with, because the gate is so sensitive, you do need a resistor down to ground, as I have here. Look, I've got a 10k from the gate back down to ground to stop any inadvertent switching on and off of this device. I mean, I could just put my finger on here and it would switch on. Sorry, you want me to show you? All right then. Right, I've switched the bulb back over again, so it's running from the MOSFET. I've taken out that 10k resistor that went to ground, and now if I touch the gate via that resistor, see, just me touching it is enough to trigger it. So that's why you normally have some high level resistor to ground. It might not be 10k, you might get away with 100k, but in my experience you do need something. Right, back to Wikipedia then. Right, what else does it say then? It says no, yeah, okay, currently we've done that bit. MOSFETs, unlike PN junction devices such as LED, can be paralleled because resistance increases with temperature. That is true, of course. You can put multiple MOSFETs together, literally pin 1 to pin 1, pin 2 to pin 2 and so on, to get more current capability. So on this particular setup, I could have put 2 of these in parallel to double the current sinking capability to bring it more in line with this one. In practice though, I get a feeling you just use a different transistor, I've got to say. So the main disadvantages then of FETs over bipolar transistors, which is what we're talking about when we're talking about 2N222s and BC548s, it says susceptibility to cumulative damage from static discharge prior to installation. Tell me about it. You may have noticed that when I first started this video, I had a box of stuff over here. Let me just take that other camera off. So I had my MOSFETs over here, and I thought, how am I going to get one of these out to show you? Because every time I touch one of these, it blows up, quite literally. Talk about static sensitive. That's why they all come in these, well, either static bags or these static protective cases. When I ordered some of these some years ago, they all fell out in one go, and I started picking them up, putting them back in, and at least 3 didn't work after that, just from me touching them. And previous to that, they had worked. So I looked it up on Google, and they do say static discharge into the gate of these devices can be absolutely fatal. So that is a big worry, if you like. What else? It says circuits with external gate exposure require a protection gate resistor or other static discharge protection. Well, funnily enough, that's what the 10k resistor to ground was also providing, as well as keeping the gate switched off until it had a proper 5 volt input. It was providing that protection so there was no static anywhere near it that wasn't automatically being shunted to ground. And finally it says the main disadvantage is non-zero ohmic response when driven to saturation. Well, we know that because it's a maximum of 6 ohms, but my particular sample might be down to 2 ohms. There's no real way of measuring it as such, as compared to a constant junction voltage drop in a bipolar junction transistor. Well, that's true. You're always going to get that junction, the voltage drop between the collector and the emitter on the BC548. I think it's going to be constant across it. Although why that is a disadvantage, I'm not 100% sure. So, do we say that we should be going down the MOSFET route? Do we say we should be sticking to the BC548 silicon transistor route? Well, the circuit is the same pretty much. I really should draw in on this diagram though to make it complete that other resistor. So there we are. I've called this 100k, but maybe 10k is what you require. I don't think it matters too much as long as you're not sinking too much current down here, because this thing itself will not take current down there, as you saw in the spec sheets. It's very, very, very low in currents, high impedance basically. Well, while we ponder about why we should or shouldn't use those in the future, let's have a look where I got these from. Right, you can get 10 of these then for $1.32, which is about £1 these days. That's pretty cheap. And indeed, what attracted me to them, I must admit. Okay, if they're cheap, $1.32 for 10, what about the equivalent of a BC548 or something like that? Let's have a look. So I looked up 548, they didn't have them, but what they did have was, I think it was a 547, which is pretty much the same. Slightly lower noise maybe. We can get 100, we don't want 100, we just wanted 10. So here we are, BC547, that would be a good one. Let's have a look at that. So you can get 10 BC547. I don't know why it says 557. Does it mean you get 10 of each? No, probably they probably choose. These are pretty much the same though as the 548. There's a minor difference, but $1.75. So it's a little bit more expensive. We're talking pennies now, aren't we? I don't think that's going to stop a project in its tracks one way or the other. So if cost isn't an issue, then the two devices are similarly priced. This has got a very low forward resistor drop when it's triggered on, 5 volts. This one works anyway, which we know just by triggering it. It does require a little bit of current in the base, 2 to 3 milliamps maybe, and that's about it. I don't know. I still don't know. Let's carry on reading. So this is the spec sheet for the BC548 family and applies to most. The collector emitter voltage maximum is only 30 volts. Let me make that a bit bigger. So that's 30 volts, and I know from experience that the 2N7000 is higher than that. That's 60 volts. But once again, you could probably find an NPN transistor that would stand the complete 60 volts as well. While we're here then, 200 milliamps, 60 volts, RDS on, 5 ohms it says here. However, in the actual spec, I think it says a maximum of 6. So what you're looking for with the MOSFET is the RDS on, so this one here, and that says a maximum of, well, 6 ohms if you're driving it with 4.5 volts into the gate. Well, we're driving it with 5 volts, which is what your Arduino could do, which means you'll have a maximum 6 volts. Maximum though. It's a pity they don't give you the minimum or a typical value rather than the maximum. Now if you were to drive with 10, the maximum would go down to 5 ohms between the drain and source. Not a huge difference frankly. And if I was to up the gate voltage then, do we see any difference? Let's have a go. Right, there we are. That's running now still the 5 volt gate voltage. Now I'm just going to lean over and turn my second power supply up so that the gate voltage increases. Now we're still taking 210 milliamps. Let's switch that camera back on. There we are. Position it. Now I'm going to up the gate voltage then. 6, 7, 8, 9, 10. That's now 10 volts on the gate. That's what this is supplying. And it's still 210, well, that's a change, 209 now, milliamps. So basically it doesn't seem to matter whether it's 10 volts or indeed a much more Arduino friendly 5 volts. Oh, right, so there it is, exactly 5 volts again going into that gate. And well, the current has actually gone down to 207 now, but then again, considering we're actually overrunning the capability of this transistor at the moment, is it hot? It's getting warm now, I've got to admit, it is getting warm. We are beyond its specification, so we're lucky it hasn't gone kapoof and the magic smoke come out. Right, and one final thing just before I go. If you're going to drive a relay coil here on either of these circuits, please do remember the back EMF protection circuit that you need by putting a diode in here and here the same, because the coil, when it's de-energized, will try and put its stored voltage back into the circuit and it'll have nowhere to go. We've actually covered this in other videos, but very briefly, if you have a power supply like a battery and it goes via a switch and you have a coil and then nothing, so it's just going around in a big circle, at the instant of closing your switch the coil has impedance and it resists the flow of current, but eventually the current does flow. But when you then open that switch, the energy is still stored in this coil, the coil being the coil of your relay. It's really stored in there. Now it only takes a fraction of a second to dissipate, but when you open that switch it's got nowhere to go, that energy. So without this protection diode it would try and come back into here and destroy this transistor or this one, or indeed your Arduino. However, by putting a protection diode across here, the energy which has gone into here can continue to rotate up now the diode and back out that way, even though the switch is opened, and just go round for a fraction of a second. I don't know if it's like nanoseconds or quarter of a millisecond. I've never actually measured it myself, but at least the energy has got somewhere to go, and the amount stored in here, as I say, is tiny, but it's enough to destroy your transistor or indeed your Arduino. So that's why you need this protection diode across all coils. Okay, that just brings us into this little discussion on whether we should be using MOSFETs in their TO92 format or stick to the BC548. At the moment I have a definite leaning towards the BC548 or equivalents, because they're just so much easier to handle. I've never destroyed one of these, not by handling nor by soldering, but as I say, I have managed to destroy some MOSFETs in my time. And given that the advantages seem to be fairly slim between the two, even cost-wise, I'd stick with the standard NPN transistor rather than the MOSFET. But I'd like to know what you guys think. If you've used these particular MOSFETs or can think of a reason why you would use these, please put them down into the comments below. I love reading your comments and answering them. And sometimes there's quite a robust exchange of views, but that's all to the good. That means we're engaged in the subject matter. So I'd love it, and of course YouTube loves it. Loves it almost as much as you watching the ads, I guess. Okay, that's the end of it. Thanks very much for watching, and I'll see you in the next video. I hope you're finding these videos useful and interesting. There are plenty more videos to choose, and a couple are shown below. And if you'd like to subscribe to this channel, just click on my picture below and enjoy the rest of the videos. Thanks for watching.